This one is always a bit of a hard sell at first, but it is just a notation trick, and we're going to use the exponent laws to try and point out that this thing, the radical, is just an exponent. Now, I'm just going to pop that up there and let you look at it for a minute. If you have a radical base 2, you can use exponents to write that same thing using the exponent 1/2. If you have a radical base 3, you can use exponents to show that, like so. If it was a 4 here, you'd have a 4 there. 5 here, 5 there, etc. on the way down. So that's just a fact. That's where we need to get to. You need to sort of accept that that is true. Now, for me to try and convince you, I'm going to start with the square root of 9. No, that's 3. Okay, so we already know that. That's not hard. I'm going to multiply it by another square root of 9. Well, that's just 3. So if you look at these two lines, the square root of 9 is 3. Square root of 9 is 3. I know that 3 times 3 is 9, so the square root of 9 multiplied by the square root of 9 should also give me 9. No, again, that's just fact. This line here, you could rewrite that as the square root of 9 squared gives you 9. Because like we've done in the algebra sections, the radical is undone by a square. So the only thing that would be left would be this number 9. Okay, that's the easy part. I want you to remember this particular exponent law. If you have an x squared times an x cubed, that's an x times an x times an x times an x times an x, which is x to the 5. 1, 2, 3, 4, 5 of them all multiplying together. Now you've been shortcutting that by saying, well, there's 2 here, 3 here, so that must be 5 in total. I want to use that same exponent law to look at this. So this is saying that x, square root of x, multiplied by the square root of x should be just x. Well, what's the exponent on this x here? There's only one of them, so that's x to the 1. So this rule here, take the exponents, add them, and you get this. I need a number here and a number here so that this plus this equals 1. And because they're both square roots, the exponent I put on it has to be identical because they were both square roots. So I need something here and I need something here. You make those smiley faces, not zeros. So that this exponent plus that exponent equals 1. And the only way to do that is if this is 1/2 and this is 1/2, so that 1/2 plus 1/2 equals 1. You have this other exponent law up here. If you had x cubed to the power 4, that's x cubed written 4 times. So 3 and 3 and another 3 and another 3 gives you 12. So you would shortcut that with 3 times 4 is 12. Use this same setup here, but with an x. The square root of x squared should be x. Well, I need an exponent on this thing so that that exponent multiplied by 2 gives you 1. And the only number that that works for is 1/2. It's 1/2 times 2 gives you 1. So replacing a radical with a fraction exponent satisfies this exponent law, the one where you add them because you're of that setup. It also satisfies this exponent law. So if you can use all the exponent laws without breaking any rules using a notation like that, then that notation is perfectly acceptable. So if you ever see something to a fraction exponent, it's just another way of writing a radical, a square root, cube root, fourth root, whatever. So we're going to use that little fact there to try and reduce some expressions. So the first one I've got for you here is a fourth root of 3 and a fourth root of 27. Now, if you put those into your calculator, fourth root of 3, you get something horrific. And if you put the fourth root of 27 in, you also get something horrific. But I'm going to use this notation here to replace these fourth roots. So that would be 3 to the exponent 1/4. This would be 27 to the 1/4. And from what you've learned about exponent laws in the previous sections, that's the same as a 3 multiplied by 27 all to that exponent, because the 3 gets a 1/4 and the 27 gets a 1/4. If you sort of factor it, I'm not sure factoring is the right word, but factor-ish it like this, you end up with 3 times 27 in that bracket, which is 81. Now, if you type that into your calculator, you're going to get a clean number, because 3 times 3 is 9, times 3 is 27, times 3 is 81. So 3 to the power 4 is 81. Apply this particular exponent law, keep the base. 4 times 1/4 would be 4 times 1 divided by 4 is just 1. So the value of this is 3. Now this line and this line, that's not necessary. You can just put this into your calculator and see if it comes out clean. If you don't like the fraction notation in the exponent, you could write this line as the fourth root of 81. You can flip-flop between these notations, the same way that you are allowed to flip-flop between a negative exponent and a thing in the denominator. Okay, I'm going to clean that off, and we'll try another one. We've got some things with exponents on them inside of a radical. Now the whole idea here was you can just write this radical as a bracket with a fraction exponent. So I see a 6 here. You need a bracket, put all this stuff inside, and a 1/6 goes out here. All right. Well, if I apply that 1/6 to y to the 18, I have to do 18 times 1 divided by 6. So that gives me 3. So that ends up as y cubed. X12 gets a 1/6. So you take 12 times 1/6. 12 times 1 is 12. 12 divided by 6 is 2. So I get x squared. So that gross expression there with the power 6 root can be reduced down to just y cubed x squared. If you can flip to this notation and then see that it applies just like every other exponent law does. We've got just numbers in here, trying to take the fourth root of 625 over 16. Well, using this change, that's just 625 over 16 to the exponent 1/4. Just like in all the other exponent laws, if you have a thing in a bracket with an exponent outside, that exponent applies to everything inside. So I'm going to have a 625, the 1/4, over top of a 16, the 1/4. Park that in your calculator. 625 to the power 1/4 is 5, because 5 times 5 is 25, times 5 is 125, times 5 is 625. So 625 is 5 to the 4. Apply a fourth power radical to a fourth power exponent, and they neutralize each other, leaving just the base behind. Try this in your calculator as well. 16 to the 1/4 is 2, because 2 times 2 is 4, times 2 is 8, times 2 is 16. So again, I've got powers of 4 in those numbers. So I can reduce this thing here down to 5/2. So this is maybe the more useful application of what I just did. If I take the last example and I do it backwards, I end up with the radicals on top of each other. And this I can't take a cube root of. You can try it. Definitely can't take a cube root of 3. But if I use this notation change, on top there I have 192 to the exponent 1/3, and I have 3 to the exponent 1/3. Well, that 1/3 has been applied to everything in this fraction, so I could just shorthand it like this. So think about that. If I were going the other way, I would apply this exponent to everything. So if I go backwards, I just peeled it off everything. Now 192 divided by 3 is 64. And if you park this in your calculator, you end up getting 4 as an answer. Now again, I'm trying to neutralize a third radical, so I need some number that's cubed. And 4 times 4 is 16. 16 times 4 is 64. So 4 cubed is 64. So the cube and the base 3 radical undo each other, and I'm left with just that number. So this one was a touch handier because I had two things that I couldn't write as clean numbers in this setup. By using the exponent laws, I was able to get those numbers in a place where they could actually interact with one another. I was allowed to do the division, and then I ended up with a number that could actually be done cleanly with a cube root. And that brings us to the most common and most useful application of this idea, and it's reducing a radical. So this number here, 50, I'm going to just take a look at it from a prime factoring point of view. So 50 is the same as 2 times 25. Now, I can't divide 2 by anything other than itself, but I can divide 25. So this number here, 50, is the same as 2 times 5 times 5. So I'm just I'm going to write this in my radical for a moment. I'm going to write the 5s first for a reason you will understand in a moment. Now, looking at that there, 5 times 5, that's 5 squared. So why does that matter? Well, I've got a square inside a square root. And those two things should undo each other. But this 5 squared has a 2 in there with it. So we've got to find some way to tease them apart so that the 5 squared is in a radical just by itself. So the 2 isn't interfering. And that will allow the radical to be neutralized by this square. So I'm going to use this notation here. So instead of a square root, I wrote fraction 1/2. Exponent laws say the 1/2 acts on everything. So take your 5. 2 times 1/2 is just 1. And 2 to the 1/2 would be like so. Now this number here, 5 to the power 1 is just 5. And 2 to the exponent 1/2, well, that's a square root 2 that I can't do anything with because that's a prime number and it doesn't square root cleanly, and there are no other bits to try and multiply in or divide out to try and tidy it up. But what I've managed to do here is take a number like the square root of 50, and I've been able to split it into what is that as a natural number, like an integer, and then the basic radical piece. So this number 50, it doesn't square root nicely because it has a factor of root 2 in it. The 5 comes out clean. It's just this little chunk that makes it ugly. So if you end up with something in some expression sometime where you have to do this, and you can look at that number in the top, do this in your head, and say root 50 is the same as 5 root 2, then this root 2 that you extracted from the root 50 will divide out this root 2 in the denominator, and you're left with just 5. It's just a clean number. So it's possible when you get a bunch of radicals intermixing with each other, if you can isolate this tiny little radical ingredient from that number, split it into numbers that are simple and into numbers that are irrational, then it's possible those irrational parts will divide each other away and you're left with just the integer values. So to sort of summarize how I got here, I was handed a number inside a radical. I took that number and I did some prime factoring on it, and I looked to see if I could write any of the bits to the same exponent as that radical was trying to apply. And if I could do that, then I was able to reduce it. So I'm gonna clear this off. We're gonna try another one. Okay, so square root of 500. And I'm gonna take this number, and I'm gonna try and prime factor it. So 5, that's 5 times 100. Now 100 splits as 2 times 50, and 50 splits as 2 times 25, and 25 splits as 5 times 5. So if I look at this here, I'm going to replace 500 with this horrible string of numbers here. 2 times 2 times 5 times 5 times 5. Well, I can write this as 2 squared. And I can write this as 5 squared. And then I have this extra 5 kicking around. And all that is still inside a radical. And if I write this radical in my fraction notation, I can see by exponent laws that the half acts on 2 squared, leaving 2 behind. The half acts on 5 squared, leaving 5 behind. And the half works on this 5, but there's no squared to neutralize that one. So when I look at it, these pieces were able to come outside of the radical. 2 times 5 is 10. And this piece has to stay inside the radical. So this number only gives you an ugly square root because it has a factor of the square root of 5 in it. So if you can pull that out, this is the lowest radical value that's buried in there. Everything else was tidy, so you could pull it out. Clean this off, we'll try another one. So we're going to try 500 again, but this time it's in a cube root instead of a square root. So I'm going to redo the prime factoring just so we can see this from scratch. 500 is the same as 5 times 100, which is the same as 5 times 2 times 50, which is the same as 5 times 2 times 5 times 10, and that's the same as 5 times 2 times 5 times 2 times 5. That. There we go. So I can replace that number there cube root of 500 with a 5 times 5 times 5. That's a 5 cubed. And a 2 times 2. That's a 2 squared. Now, flipping into this notation here, 5 cubed, 2 squared to the 1/3. If it's a cube root, you use a 1/3 as your fraction. 1/3 acts on this. 1/3 of 3 gives me 1. 1/3 of 2, well that's 2 times 1 divided by 3, and that doesn't go cleanly. So it's going to look like this. Gross. But if I look at what I've got here, I've successfully neutralized the cube root on this chunk of the number. So I have 5. I'm going to need a radical because I have a root here, and it's going to be a cube root. So that's a 3, that's a 3. And that leaves 2 squared inside here. Now, you may prefer to look at that as 4. 2 squared is 4. And at any point in all 3 of those lines, you have successfully extracted an integer value out of this cube root. So if that form is, if you're okay with that form, leave it like this. If you're okay with this form, leave it like that. If that form freaks you out and you're more comfortable with this form, then write it like that. They're all equivalent. So once again, I've managed to take a number that doesn't have a clean cube root, and I've been able to extract the pieces that can be cube rooted, leaving only the residual piece behind. So the last one here to look at, and then we'll let you go try the practice problems. You're going to try the cube root of 108. You can try that on your calculator and it won't work, it gives you something awful. So I'm going to take this 108 and I'm going to do the prime factoring on it. So I see it's even, so I can cut it in half. That would be 2 times 54. You can see that 54 is also even, so I can pull out another factor of 2, leaving 27, because 2 times 27 is 54. And 27 divides even, it's not even, so I can't pull out a 2, but it does divide evenly by 3, so I can pull out a 3, that's 3 times 9. And 9 is 3 times 3. So this number, 2 times 2 times 3 times 3 times 3, gives you 108. I'm going to take this, I'm going to put it in the radical here. Instead of 108, I'll put in its prime factoring. I'm going to shortcut this as 3 cubed. I'm going to shortcut this as 2 squared. So acknowledging for the last time that a cubed root is just the same notation as a fraction exponent, with a 3 in the denominator. My exponent allow me to apply this to this, leaving only 3 behind. I can apply this to this, which gives me 2 to the 2/3. And at that point, I have successfully extracted all the integers I can. If you don't like the fraction notation, this literally says a cubed root with a 2 squared inside of it. And if you don't like having an exponent inside a radical, you could write that as cube root of 4. So when you're presented with a number inside a radical like that, and there's no division or multiplication to do to try and simplify it, try the prime factoring, because you may be able to find a triple set of some number that will neutralize the cube, or a double set that would neutralize a square root, or a quadruple set that would neutralize a 4th root, etc. This is abstract. It causes a lot of heartburn every year, so just take a deep breath, give it a try, see how it goes.